Hello everyone, and welcome to this talk about pressure relief for heat exchangers. I am Maurice Worthington, Vice Chair of the IMechE Process Industries Division, Northwestern Centre, and I will be chairing this event and the QA at the end. Please submit your questions throughout the event and we will direct them to our speaker later. The webinar is being recorded and made available on demand along with the presentation slides. I would like now to introduce our speaker, John Whitaker, who is a Senior Process Engineer at ABB Limited. So over to John for his presentation.
Okay, thank you very much, Maurice.
Thank you.
My name is John Whitaker. I've got about 15 years of industrial experience, largely in the oil and gas industry, both upstream and downstream. I'm a chemical engineer by background, process engineer now. I've been working for ABB for about 2.5 years, and in that time I've had a chance to work in other industries such as chemical manufacturing, pharmaceuticals, and others. So thanks very much for having me today. Today's presentation is about pressure relief considerations for heat exchangers. So to run you through what we're going to talk about today, so I'll give you an introduction to the topic. We'll go through the various types of heat exchangers, give you an overview on that. We'll identify pressure relief cases for heat exchangers, and this will focus largely on the main ones, which are fire, heat transfer between streams, interstream leakage, and tube rupture. Tube rupture cases are well recognized for conventional shell and tube heat exchangers, but we'll also talk about other types such as plate and frame exchangers. Later on, I'll cover the most recent guidance on tube rupture from the Energy Institute. There'll be various case studies interspersed throughout the presentation, which will hopefully be interesting. And then there'll be a summary at the end. This presentation is an overview of the subject area and will hopefully inspire you to think a little bit deeper about it. So heat exchanger types. On this slide, you'll see a picture of a conventional shell and tube heat exchanger where you've got processed material going to a shell, and then another process stream going to the tubes of the exchanger. And those two process streams are kept entirely separate, but there's energy transfer between the two of them. So I think most of you will probably be familiar with this type of equipment. So what other types of heat exchangers are there? Well, there's the double pipe, there's a shell and tube, as talked about before, plate fin exchangers, printed circuit heat exchangers, plate and frame, spiral wound. Fired heaters are a type of heat exchanger when you use a more broad definition. You've got air coolers, sometimes called fin fan units. A jacketed vessel, again, is a type of heat exchanger. You may also have coils in vessels that can be used for heating or cooling. And you also have steam and electric tracing, and this is not usually used for process stream heating, but it's still a potential heat source, so may need to be considered in terms of pressure relief when we're thinking about pressure relief for these types of units. So heat exchangers may be used for heating, cooling, condensing, or vaporizing of process streams, and you can have liquid, gas, or two-phase flow on either side of the exchanger. So there's a lot of flexibility in these types of units. So heat transfer doesn't just occur where we have two separate fluid streams. It also occurs where there is direct contact between the fluids. It could also be due to ambient changes in the environment impacting the process. So for example, you could have direct mixing in a vessel or tank due to quenching, mixing of streams such as in demineralized water tanks, mixing of material in storage tanks, chemical reactions which may give way to heat being produced by the reaction, energy changes in the process. And as before, we have ambient changes such as solar gain from the environment and natural temperature changes impacting the process. And a key example of that would be the breathing in and out of a low pressure storage tank to account for those ambient changes. So we'll need to consider pressure relief in these scenarios. So in this section, we'll talk about how to identify pressure relief scenarios for heat exchangers and review some typical cases that come up again and again. So it's best to use a structured approach to prompt thinking in order to identify all the pressure relief cases that may exist in the system you're looking at. So a key rule to be remembered is if inflow of mass or energy is greater than the outflow, then pressure will rise. And conversely, if inflow of mass or energy is less than the outflow, then the pressure will fall. And that's a key rule that applies to all sorts of process equipment, not just heat exchangers. In terms of the methodologies that we'd use to go through this structured approach, there's various types of methodologies out there that can help. So there's a checklist in API 521, which is useful. You may have in-house company procedures for identifying cases. You can use HAZOP or hazard identification studies to identify overpressure and relief cases. And with ABB, we have the document that we rely on, EP-Sheg 8. And Table 1 in that document is our recommended methodology for going through this structured approach to identifying overpressure cases. In reality, it's not hugely different from the checklist in API 521. So the fundamental thing to remember about heat exchangers is that there are two separate systems involved. So you have a high pressure side and a low pressure side, and they're separated by a metal interface. When considering pressure relief requirements, you need to consider each side separately and consider the internal and external pressures for each of those sides separately. Also consider what happens in the event that the interface between the streams fails, in the event of a barrier failure, so the interstream leakage scenario. And then you can get mass flow from one system into the other, heat flow from one system into the other, and you could have things happening like unintended chemical reactions when those streams come into contact with each other, which was never part of the design intent. And in a full tube rupture, you'll of course get mass and energy going from one side of the system into the other, assuming they are at different pressures. So on this slide, I'm showing a matrix approach. This is from EP-Sheg 8, and this is a way of sort of going through the structured approach to identify overpressure cases in your system. So this is just an example, and you would always just apply this methodology to your individual situation. So on the rows, we have plant conditions, such as blocked-in equipment, restricted outlet, restricted inlet, or a chemical reaction occurring. So that's a condition on the plant before an event occurs. And on the columns, we have events then that could take place. So we have things like fire, an external fire, say a pool fire, a process abnormality, such as reverse flow taking place for some reason, or an equipment service failure, such as interstream leakage. So the heat exchanger has actually failed internally, so that you've got material going from one side to the other, or it could be something like a control systems failure. Also, you could have an event like a simple case of ambient conditions changing. So solar gain moving from day to night or night to day, and situations related to the ambient environmental conditions. So what you're doing is you're thinking about the plant condition and thinking about the events that could occur when that plant condition is in effect, and thinking about what overpressure could result from those scenarios. So that's a structured approach to working out those relief cases. So typical relief cases to consider are fire if you have flammable materials, heat input to one system causing thermal expansion of the material, and tube rupture and interstream leakage, as has been mentioned a couple of times already. But there may be others as well that are not as obvious as these, so that's why you need the structured approach to try and make sure you pick everything up. Interstream leakage, though, is normally the defining or controlling case, but not always. By controlling, I mean the largest case, or the most onerous in terms of deciding what your relief system needs to be to cater for that case. So you may find that different cases give you completely different relief loads, and that may lead you to have different relief devices to cater for different relief loads. For example, the thermal expansion case can often be quite a small relief flow, but for a tube failure, you could end up having a much larger relief device needed. So you may, for example, have a small relief valve for a thermal expansion case, and then a much larger relief valve or bursting disc for the event of tube failure. And if you set the pressures differently between those two relief devices. For example, you could have the thermal expansion case with a set pressure lower than the point at which the bursting disc or the relief valve would open for tube failure. Then you can avoid disturbing the larger relief device when in the event of the smaller relief case happening. So you could allow that thermal expansion relief flow to leave via the relief valve without having your bursting disc opening at that point and then having to deal with recovery from that bursting disc failure. So you consider the differences in set pressures between the relief devices to cater for your different relief events that you've come up with following your structured approach to working out what relief cases you actually have. So first case study here. So this is an example of why you need to consider in a heat exchanger system the two sides of the system to be separate. So here we have a steam heated vessel with a jacket and steam going into the jacket to keep the temperature up in the vessel in normal operation. And we have steam going into the vessel via a restriction orifice plate, and condensing in the jacket and leaving as a liquid, as condensate. There's also a vapor outlet line to a relief valve, which is shown on the right-hand side there on the schematic, and an automatic air vent there as well. So what happened here was that the RO was inspected, but it wasn't refitted after the inspection, and the plant was, or the equipment was brought back into service. So because there was no restriction orifice in place here, as there would normally have been, there was a much higher steam flow into the jacket, and the relief valve had been designed assuming that RO was always going to be in place. So that relief valve was now undersized for the amount of steam flow coming in to the vessel. So it opened to try and relieve that pressure that was rising because of all this steam flow coming in, and unable to leave anywhere else. But because the RO plate wasn't there, the relief valve wasn't big enough to deal with that flow. So the pressure continued to rise in the jacket. And what happened was that you ended up with the pressure in the jacket, which is the external pressure from the point of view of the vessel. So that pressure got so high that the vessel wasn't able to deal with it, and the vessel actually collapsed in this case. So external pressure on the vessel caused the vessel to collapse and cause quite a lot of damage. So that's just a reminder to consider the two sides of the heat exchanger system to be separate, and think about them separately to identify what could go wrong in a process. So let's move on to fire. So fire cases are normally fairly straightforward. So the heat input from a fire is based on the wetted surface area for the vessel, and this applies to any sort of process equipment. So in a heat exchanger, you'll be thinking about the wetted surface area for the shell. So that's the surface area internal to the shell that's going to have liquid there that may be being heated from the fire that's external to the shell. So then you've got this energy transfer from the fire into that liquid, and then it will obviously increase its energy, and it may boil. So in terms of the shell, you would think about what could be going on there. So could it be full of cooling water? Could you have what would the maximum level be there? It's a kettle reboiler, or is it actually free draining? So there wouldn't be any liquid there in the event of the fire. So you have to think through what's actually going to happen in this event. With regard to the tubes, you may still be concerned about the tubes receiving heat input from the fire. So you would consider whether heat may also be transferred from the shell through the surface area of the tubes into the tube process stream. So that's really thinking about a shell and tube heat exchanger. So for a plate fin exchanger, these are normally actually well insulated. If it's a free draining piece of equipment, then you won't have liquid hold up, and there'll be no actual wetted surface area. So there'll be no heat input for the fire. So in that case, you can eliminate fire for this type of heat exchanger. But as with anything else, you need to think through what is your scenario of your particular item of process equipment. So continuing with fire, as always with pressure relief, you would normally take a pessimistic approach. Think about what's the worst case that is still credible. So for a jacketed vessel, you would consider what's the maximum liquid level that could be there in the jacket, because the more level, the more wetted surface area you have, and the greater relief flow you're going to have, and therefore the greater size of relief device. If you're thinking about the vessel underneath the jacket, then you'll have a different approach, and you'll think about the bare vessel, because the jacket could actually, in the event of the fire, it could fail, it could empty of the liquid or whatever material is in the jacket, so you lose the protection there, or the jacket may just be badly damaged by the fire and may just fall off the vessel, leaving the vessel bare. So in each of those scenarios, you're thinking about what's the worst case. For a fin fan cooler, you would use the bare tube area, because although you're going to have fins on the tubes, those fins may be destroyed quite quickly in the fire and therefore offer no protection after that point. You would neglect any cooling from convection, because that's going to be pretty negligible compared to the heat input from the fire. And you would consider the adjoining pipework, in any case, up to the extent of the fire zone boundary or up to the next isolation valve. And that applies to all sorts of process equipment, not just heat exchangers. That's how far you would go. So you would obviously include a little bit of pipework connecting onto your vessel or heat exchanger or whatever it might be when you're thinking about the fire input case. Moving on to heat transfer, leading to overpressure. So the key question here is, if your exchanger is blocked in, can the hot side cause an overpressure in the cold side? So the energy from the hot side moving on to the cold side, which is blocked in, can that cause overpressure in the cold side? This could also be caused by ambient changes, so solar gain from the environment. If you do have the cold side being heated in this case, you could have thermal expansion and expansion of the liquids, or you could also have enough energy input to boil the liquids, which will obviously then lead to vapor and quite a quick rise in pressure. So that's normally going to be more onerous than the thermal expansion case. In the schematic on the slide, we've got isolation valves showing on both the inlets and outlets to the shell and the tube side of the exchanger. So if you're worried about the cold side being overpressured from heat transfer, something you might want to think about is, do you actually need the isolations on the cold side? Because if you've got those isolations there, then you've got potential for those isolations to be enacted, for the valves to be closed, and that could be done inadvertently by an operator error or anything like that. So if you actually were to design out those valves and just not have them there, then there's no way for that to happen, and perhaps the cold side, it wouldn't be possible to block the cold side in, so you could actually eliminate the relief case in that way. So always just ask yourself that question: do you really need those isolation valves? If you have a system that has steam in it, or a system that is cleaned with steam, perhaps, you would normally design for that side of the system to be good for full vacuum. And that's because if it's blocked in with steam there, then as the energy is lost to the outside environment, the steam will lose that energy, and it may then cool and condense. And if it condenses, because you've got a fixed volume, you're then pulling a vacuum as the steam collapses, because obviously the liquid water isn't going to take up as much space as the steam. So in that event, you're likely to pull a vacuum, and if your system isn't designed for that, then you could actually collapse your process item in that case. So on to another case study. So this is an example of an event that occurred that caused one fatality and 6 injuries. So pretty serious. Here we have a heat exchanger, and on the pink side we have the process stream, and on the green side we have the cooling stream, which is actually an ammonia stream. So ammonia liquid comes into the heat exchanger as a liquid, and with the energy it removes from the process stream, it's then heated up, so it leaves the heat exchanger as a vapor, and normally it passes on to the cooling system via the pressure control valve. There's also another outlet line for the ammonia vapor, and that's to a rupture disc and relief valve. So what happened in this case was maintenance work was being carried out. The rupture disc on the ammonia side was isolated for change out, so it wasn't available. The pressure control valve on the outlet line for the ammonia vapor was also blocked in via the block valve shown on the schematic. So in fact, there was nowhere for the ammonia vapor to go. And the process side of the exchanger was being subjected to steam cleaning. So there was steam in the tube side of the exchanger, and then therefore there was energy going from that steam into the ammonia. The ammonia, that vapor that was caused by the boiling from the energy from that steam, the ammonia vapor had nowhere to go. It was completely blocked in, and that resulted in overpressure of the ammonia side of the exchanger, and we had an explosion. And as I say, there was 1 fatality and 6 injuries there. There's more details on this on the Chemical Safety Board website, which is a US government website where they record the incidents and learnings from incidents in various industrial accidents that have happened in the US. So you can learn more about that incident there. So the example on the previous slide, the case study, was based on ammonia being vaporized under heating. But thermal expansion can cause a large rise in pressure even without a change in phase. So this slide shows different thermal expansion coefficients for different fluids. So we've got chlorine, hexane, water, and kerosene. You can work out the coefficient of expansion based on looking at the densities at 2 different temperatures, and you can work out what that expansion coefficient actually is. So as you can see from those coefficients, the most onerous one is chlorine with the highest coefficient, and the lowest one is water. But in the case of solar gain, where you've got a pipeline being warmed from the sun, really, it's actually possible to protect a very large length of pipeline with a very small nominal relief valve. So a nominal thermal relief valve would be thinking about a 3/4 inch inlet to 1 inch outlet relief valve. Just a small standard thermal relief valve, and you can protect large lengths of line with a thermal relief valve like that. So with water, with the smallest coefficient of expansion of those 4, with a 2-inch line, you could protect 158 kilometers of pipe work, and with an 8-inch line, you could still protect almost 40 kilometers of pipe work. So a very, very long length of piping. With chlorine, with the higher coefficient of expansion, it's not as much as that, but still with a 2-inch line, it's over 4 kilometers you could protect. And with an 8-inch line, it's still over 1 kilometer you could protect. So that just shows that although thermal expansion could rupture a line, you can protect a lot of length of line with just a small basic thermal relief valve. On the photo on the bottom right-hand side of the slide there, we've got different situations. So this was in the case where a pump was running with blocked-in pipe work. So the pump was imparting energy to the system every time the fluid moved through the pump, and that resulted in the material, the process stream, actually heating up gradually, and eventually you had overpressure, and that caused the severe damage you see in the photo. And in this case, the fluid was ethylene oxide, so not really something you want to be taking any risks with. So that caused quite a lot of damage. So mixing of fluids can also lead to heat transfer effects as well. This is where you have direct contact between the fluids, and of course this could arise in a situation of interstream leakage, barrier failure in the exchanger, which we'll talk a bit more about later, especially if you have pressure differential between the systems. And if this happens, you could end up with a reaction taking place between the 2 sides of the exchanger, or heating effects due to mixing. So your boiling point of the mixed fluids could be lower than that of either liquid, so you could end up with vaporization occurring unexpectedly. You'll also have the possibility of liquid layering and rollover. So this is particularly thinking about large storage tanks, such as storage tanks holding liquefied natural gas, LNG. So in this situation, you could have layers of different densities building up or collecting in tanks where there's no movement of fluids between those layers. And you could have a situation where there's more heat coming into the layer that is lower down in the tank than the upper layer. So that lower layer ends up getting heated a bit more. It gets less and less dense as it gets warmer. So you've got this buoyancy effect where it kind of wants to move above the denser layer above it, but it can't because of the static head of that layer of liquid in the tank. But if that situation carries on and the density difference continues to increase, then you may suddenly get a situation where it can suddenly overcome that static head of the fluid above it, and this is called rollover. So it will suddenly push that material out of the way and move to the top of the tank, and then that will start to vaporize very, very quickly. So you can get an enormously high generation rate of vapor in that situation, in this rollover situation. So it can be quite dramatic and lead to very high relief flows. The way to avoid that is to have good mixing in the tank, so you don't get this stratification of different layers of different densities. So you keep the layers well mixed, so you don't get different layers, and also to insulate the tank, so you don't have a large amounts of heating from the outside environment into the material in the tank. So that's quite a specific example of something that could happen due to direct heat transfer effects. So moving on to interstream leakage. So for shell and tube heat exchangers, tube rupture is a relatively rare event, but incidents have occurred, so it is a credible event that could happen. So some possible outcomes of this are as follows. You could have release of material from the shell side gaskets. That's assuming the shell side is the lower pressure side, which it normally is, but not always. Overpressure of the cooling system. Gas release from the cooling system. So the gas has come through from the high pressure side to the low pressure side, and now you've got gas release via somewhere on the cooling system, such as from a cooling tower, say. The tubes might just leak a bit, or they can suddenly fail across the tube diameter. So from fretting damage on a baffle, say, you could credibly suddenly have a full failure of a tube in the exchanger. However, you wouldn't consider it credible most of the time to have a failure across multiple tubes. So normally your worst case situation is a failure of a complete failure of one tube. So there is potential for multiple times overpressure of the low pressure side. And this means potential for catastrophic failure of the low pressure side and a large loss of containment, so a very serious incident. So for example, in the oil and gas industry, it wouldn't be particularly unusual to have 200 plus bar gas on a compressor train, on the cooler on a compressor train, on the high pressure side of the exchanger, with maybe 15 or 20 bar cooling on the low pressure side, whether that be water or some sort of refrigerant. So you've got 200 plus bar on the HP side and maybe 20 bar on the LP side, so a factor of 10 there. And then you've got this huge differential pressure, which then makes the tube rupture case very serious. This is difficult to design out, because if you wanted to make the situation or the system inherently safe, you would make the LP side good for the HP side design pressure, but because you've got this huge differential, making the LP side good for 200 bar in the example I just mentioned would be a very expensive, very costly activity to do. And it wouldn't just necessarily just be the exchanger. You would need to increase the design pressure of the LP side. You'd perhaps have to make a large part of the cooling system suitable for handling that larger pressure. So that's obviously going to have a very big impact on the cost of your equipment, and it may be uneconomical to do that. So we'll start with the case of shell and tube heat exchangers, as this is the most common type of exchanger, and we will move on to others later. So this case is determined by assuming a complete shear at the tube sheet, resulting in two open ends, and that results in flow from the high pressure side to the low pressure side. The relief rate is normally determined by completing a flow through an orifice calculation and multiplying the result by 2. So you're multiplying by 2 because you've got the two sides of the tube that's failed. So you've got a stub at the tube sheet, and then you've got flow coming out from that, and then you've also got the end of the tube that's broken from the tube sheet connection. So you've also got the flow coming through from that. So you work out the flow through one of the orifices based on the size of the tubes, and then you multiply that by 2 to get your flow that's going to come through in that event. You may be aware of the old API 2/3 rule, which is often talked about in industry, and this was based on the test pressure being 1.5 times the design. So the 1.5 is where the sort of 3/2 comes from. The theory of this is that if the maximum pressure experienced by the low pressure side is lower than the test pressure, then catastrophic failure is unlikely and the case can be ignored. So if the low pressure side test pressure is actually greater than the HP side design pressure, then catastrophic failure is unlikely because the LP side will be good for that. So this principle is still in place, this 2/3 rule. It's often talked about, but it's worth noting that ASME test pressure is now 1.3 times design, which would make it the 76% rule or the 10/13 rule. And you now need to take temperature into account when determining the test pressure. So you need to account for the temperature difference that would be in place when you're actually in that relief scenario, or in that overpressure scenario, sorry. You need to account for that higher temperature. So for BS, British Standard 5500 vessels, the test pressure to design pressure ratio would be at least 1.43. So this would give you another fraction again. This would be the 7/10 rule. So it does get a bit more complicated when you start thinking about what the actual test pressure situation is with regard to the low pressure side. So as before, you need to consider your scenario individually and not rely on sort of rules of thumb. Tube rupture may also be eliminated as a possibility based on an assessment of the failure mechanisms and a determination of whether this is actually credible or not. This will be covered a bit later in the presentation. However, it's always difficult to be completely sure a possibility is not credible, that it's eliminated. A more general point, so protecting heat exchangers from overpressure is fundamentally the same as with any other item of equipment. However, they do present the following specific problems. So the type and extent of internal failure that can be anticipated is one. Selection of a relieving device that reacts fast enough to prevent the overpressure is another. And selection of the proper location for the device so that it senses the overpressure in time to react to it. And we're particularly going to discuss this in the next few slides. So the question here is that many shell and tube heat exchangers have bursting discs instead of relief valves in terms of their relief device. And the question is, why is this? So the Energy Institute, the EI, set up a joint industry panel in the 1990s to study interstream leakage in more detail in heat exchangers. This resulted in guidelines being issued, and over recent years these have been extensively revised and updated again. And this research is still ongoing, so the guidance will probably be updated again in due course. So this is an ongoing area of interest. So testing has shown that in the case of a sudden tube rupture, a shockwave can be set up in the heat exchanger as the HP fluid, which we're thinking of as a gas. So it compresses the liquid that's in the LP side as it comes through. So you have this shockwave that takes place in the event of the interstream leakage taking place. If the relief device on the LP side doesn't then open quickly enough to relieve the pressure, then the shockwave can bounce off something in the LP side of the exchanger, say a baffle plate or even the relief valve outlet line, and it can be reflected back into the exchanger again. So you get this reflection of the surge wave, and that causes it to build in terms of that adds another surge pressure again to what you've already got. And this is a short duration transient event, so it's all happening in milliseconds. Because of this surge pressure, which is something additional to what you would just think about when you're looking at, well, what are the design pressures of my two sides of this exchanger? You can get pressure above the 2/3 of the 10/13 rule, whatever rule you were thinking about. So above the LP side test pressure. Work is ongoing to assess what the worst case pressure could be during these short-term transients. And this is, as I say, this is ongoing work that the Energy Institute, the EI, are doing. Testing and modelling done by this joint industry panel set up by the EI. So that a number of factors affect the peak pressure generated in this event. And these factors include things like the heat exchanger configuration, the pressures, the tube diameters, the shell diameter, what relief device you've got, the baffle arrangement, and so on. So lots of things related to the internal geometry of the exchanger have an impact on what the peak pressure might be in this event. So the answer to the question about why heat exchangers often have bursting discs instead of relief valves is that bursting discs open more quickly than relief valves, and they therefore can reduce the peak pressures in time to prevent the overpressure in the exchanger and prevent rupture. So on that, so the relief device opening times that are typical. So for a spring-loaded relief valve, they would open in 5 to 50 milliseconds typically. A buckling pin device, which is another type of relief device, which you don't see very often, they're a bit sort of old-fashioned, 3 to 30 milliseconds for those. And for a rupture disc or a bursting disc, you're thinking about 1 to 20 milliseconds for these. So that's quite an improvement on the relief valve, and that improvement can make all the difference in terms of relieving the pressure that would otherwise build up in the exchanger and possibly cause it to catastrophically fail. So the EI guidance criteria for relief devices is as follows, and this is in the document that they've released. So if the LP side of the exchanger, the test pressure is greater than the operating pressure of the LP side plus 2 times the initial surge pressure, and this is thinking about the surge pressure and the reflected surge pressure, that's why it's the 2 times comes into it. So if it's greater than that, then the relief valve and a buckling pin device is okay. If the LP side test pressure is only greater than the operating pressure plus 1 times the initial surge pressure, then instead of a relief valve or buckling pin device, you would need to have a rupture disc. If the LP side test pressure is actually less than the operating pressure plus 1 times the initial surge pressure, then modification of the heat exchanger design is required. So what that's saying is you're in a bad place at this point and you might need to go back to the drawing board, or you might need a whole new heat exchanger if this is an equipment item that's already installed on the plant. So that wouldn't be a good outcome. So just to go into that in a bit more in terms of an example, hopefully to demonstrate this a bit more clearly. So in an example, imagine that you've got a heat exchanger where the LP side operating pressure is 5 bar gauge and the HP side design pressure is 11 bar gauge. The initial surge pressure on tube failure is 2 bar. So looking at the left-hand side of the columns there on the schematic, on the graph, the blue is the operating pressure of the LP side, so you've got 5 bar there. Where the first surge comes through, you've got the initial pressure change, which is another 2 bar, taking you up to 7 bar gauge overall. And then with the reflected surge, you get another 2 bar, and that takes you up to 9 bar gauge overall. So on the right-hand side, you're looking at the design constraint for the LP side based on what the test pressure actually is. So if your test pressure of the LP side is less than 7 bar gauge, you're in that bad place I talked about in the previous slide. So you're talking about modifying the exchanger design. But bear in mind that if you've got an LP side with a 5 bar operating pressure, you would normally hope that the test pressure would be more than 7. But if it's less than 7, then you may need to modify the exchanger design. If it's greater than 7 but less than 9, then you'd be in the position of wanting to use a rupture disc to protect the LP side from the case of tube failure. If instead the LP side test pressure is greater than 9 but less than 11, then you would be allowed to use a relief valve or a buckling pin device if you preferred. And if the LP side test pressure was greater than 11 bar gauge, then you wouldn't have a concern and you wouldn't need a relief device at all, because you'd be saying that even if this event occurs, I'm not going to overpressure my LP side of the exchanger. So I don't need a relief device for that scenario. You may need the relief device for other scenarios that we've already talked about in previous sections. So bursting discs have tended to have been used in these circumstances rather than relief valves because of their faster response time, and that limits the peak pressure and the possibility of overpressure and catastrophic failure. So what are the downsides of bursting discs as relief devices compared to relief valves? Well, really, it's the reality that they don't reclose like a relief valve does. They're more prone to spurious failures. So if they do spuriously fail, or even if they do fail, they don't reclose. So then you're in a situation where you're losing possibly large amounts of liquid in your system to a disposal system, and that may cause you problems in and of itself. That can be an issue for the plant to deal with. And obviously, the bursting disc would have to be replaced before the plant could be returned to what it was before that spurious failure occurred. Whereas with a relief valve, it will reclose, and you're back to where you were before. So another case study. So in this one, we have a hot oil system going through the tubes of a heat exchanger, and it's coming from 2 pumps. We've got a duty pump and a standby pump, and it's sending material off to another hot oil tank. On the shell side, we have the process stream, which is a gas, and on the tube side, downstream of the exchanger, we have a bursting disc sending material into a flare system. And that bursting disc is designed for breakthrough, or it's designed for a gas duty, so breakthrough of the process gas in the event of tube failure in the exchanger. So that's what that bursting disc is sized for. So what happened here? Well, during startup, the hot oil system was running, it was activated, and the hot oil was being pumped around the system. The hot oil tank level, where the hot oil is being sent to, was not rising as expected. So operators assumed that the hot oil pump had failed. This is the duty pump. So they decided, okay, let's start up the standby pump, and then we'll see the system operate as expected. But what had actually happened was not that the pump had failed. So the bursting disc had actually failed spuriously. The hot oil was therefore being pumped through that bursting disc into the flare system. It so happened that a compressor was also being blown down into the flare system at that time. So the hot oil in the flare system was then being accelerated by this gas from the compressor, and you ended up with slug flow in the flare system of this liquid and vapor together. The pipework wasn't designed for slug flow. It caused a lot of stress in the system. So the forces on the pipework caused it to break free from the pipe supports. This forced the plant to shut down because the flare system it had broken free. It was badly damaged. This caused 6 months of lost production, greater than $100 million of lost revenue, and a lot of damage to the local reputation of the company involved. But luckily, in this case, there were no injuries and there was no major environmental damage that took place. So there are other similar incidents involving large quantities of utility fluids from an LP side of an exchanger being inadvertently dumped into disposal systems. It does happen, and in some cases this can overfill the knockout drum, compromising the disposal system. So it's important to consider the implications of a spurious failure of a bursting disc if that is selected instead of a relief valve for a relief device. So you always need to think about, okay, I do want to have this bursting disc so it can react quickly to an overpressure event, but what's going to happen if it spuriously fails, or what's going to happen if this relief event does actually occur and the rupture disc actually does rupture? What happens next? So the guidance I talked about previously is the details are given on this slide. So this is the Energy Institute guidance I was talking about. The title is Guidelines for the Safe Design and Operation of Shell and Tube Heat Exchangers to Withstand the Impact of Tube Failure. The current edition is the second edition, which was issued in December 2015. So it's not that new now, I suppose. And I believe another edition may be upcoming soon enough. You can access the guidance from the website shown there. It's free to download the PDF, or you can order a print copy. The guidance covers incident reviews, operator surveys and data collection, experimental work and modeling of tube failure events, guidance on heat exchanger design to reduce the risk of failure, such as we've talked about, design methodology for heat exchanger relief systems, both new and existing systems, and design of the wider relief system, and instrumentation selection. So it's worth noting that in some events, or many events that have happened in the past, incidents have escalated as there was no instrumentation to help the operators diagnose the situation. And that is an example of that was in the previous case study where the operators were trying to guess about why the hot oil wasn't building up in the tank as they expected it to, and they guessed what the reason was, and they guessed wrongly. So instrumentation can help the operators work out what's actually happening in a situation in a system when something's happening that's unexpected. Right. So going on to interstream leakage for other heat exchanger types other than shell and tubes. So obviously there are other types of heat exchangers, so we need to think about that event in those cases. So for a double pipe heat exchanger, the tube failure case isn't normally considered, and that's because you think about the inner pipe or the inner tube of the exchanger is really just the same as a standard pipe on the plant, and the likelihood of it failing is as high or as low as the outer pipe would be failing anywhere else on the plant. So if you don't consider it credible for a pipe to suddenly fail with loss of containment on the plant, then you wouldn't consider it to be credible for the pipe internal to the heat exchanger to fail in the double pipe scenario. So that's sometimes a design that operators will go towards if they really want to rule out the tube failure case, if they have a massive differential pressure between the HP and the LP side, and they know the consequences of a tube failure are going to be very serious, then they might go for this double pipe design to make it not credible. So that is an option. For plate and frame exchangers and printed circuit exchangers, interstream leakage should though be considered. Holes between pressure systems can potentially form due to corrosion or fatigue or erosion. Unfortunately, the available guidance here is a little bit sketchy. So API 521 just recommends considering a hole of 6.4 millimeters to 25.4 millimeters. That's a quarter of an inch to an inch in diameter, and that's not particularly helpful. It's a bit vague. So the EI guide suggests that for a printed circuit heat exchanger, the flow through one channel could be used to determine the relief rate. For plate and frame exchangers, an area of 1 millimeter squared could be used for approximating a failure due to corrosion, or 10 millimeters squared for the case of a fatigue crack. Please note that the relief flow calculation is still an orifice calculation, so it's still an orifice calculation you're doing, even though it may not be an orifice really you're thinking about. But there's only one hole you would consider, not two, as for the shell and tube exchanger rupture we talked about before. So going into a summary for the relief systems for heat exchangers. So what you would want to do is identify all your credible relief events. And as we discussed, I think more than once, the main ones are normally fire, heat transfer, and interstream leakage, although there may be others. You would specify suitable relief parameters. So you've got the set pressure of your relief device, and you think about the sizing of your relief device. You would determine the disposal system, what that's going to be, and that might be dependent on what the fluid is you're relieving. So you think about, is this fluid going to be hazardous in some way? Does it need to be treated before it's released to the outside environment? Or does it need to be, is it valuable? Does it need to be recovered? So you'd be thinking about those sorts of things. You would decide on the instrumentation for monitoring the disposal system, so you can work out what's actually happened in a relief event, and the operators can work that out in real time. You would determine the required response time, and from this, what the most suitable relief device type is. So again, we're thinking about the transient event in the tube failure case really here, and whether you want to go for a rupture disc because it's going to react more quickly in that event than a relief device, or a relief valve, sorry. So the more general summary now. So for heat exchanger relief systems, the protective systems must be carefully defined, and always consider the interactions between those systems. Consider the internal and external pressures of each side of the exchanger, each system. So for example, for the tubes, the external pressure would be the shell pressure, and of course for the shell, the external pressure would be the outside environment pressure. So think about those internal and external pressures and how they apply to which side of the system you're looking at. Consider relief scenarios in all types of heat exchangers and other heat transfer systems. And in terms of identifying those relief scenarios, you'll follow a structured approach using probably a matrix, such as an API 521 or the PSHEG 8 table. You design a suitable relief stream disposal system for your relief cases, if you have them. And for shell and tube heat exchangers and the tube rupture case, always consider the EI guidance on those tube rupture cases, because it's the best guidance available, and it's more than you'll see discussed in API. So the question I'd like to leave you with is, are your heat exchangers and heat transfer systems provided with adequate pressure relief? So this question, of course, applies more to those of you who work on operating plants and actually have heat exchangers that you need to think about and wonder if the relief systems on those exchangers are actually adequate. So thanks very much for listening today. My contact details are shown below, and you can contact me on that phone number or on my email address. If you've got any questions for me that may come to mind sometime after the presentation or at a later date, that's fine. So once again, I'd just like to say thanks very much for listening to a chemical engineer today. That's much appreciated, and I hope you've enjoyed it.
John, thank you for the presentation. We've got some questions for you to answer, and I'll go into these right away. A question from Ross Finlay. Where could one find a methodology for calculating solar gain in pipework to facilitate relief valve sizing? And I was thinking that your slide 18 showed some of those details.
Yes, that's right. So that methodology for solar gain is actually given in API 521. So that's the best guide for those thermal expansion cases, and it will tell you the key thing is to work out what your worst case heat input would be, and that will for thermal expansion for solar gain, that will depend on whereabouts in the world you are. So of course, if you're somewhere far from the equator, you may have less worst case heat input from the environment on a hot day than if you would have if you were somewhere, say in somewhere near the equator. somewhere in a hot environment or a desert. So that will affect how much heat input you would have to your system. And you would also think about what's the worst case temperature you could get to from that heat input. But the methodology is given an API 521. That's the guide to look at for that particular relief case.
All right, thank you. We've got one from Christopher Hurst, and he said, on the ammonia case study, the relief system has an isolation valve between the heat exchanger and the bursting disc stroke relief valve. Is this allowed in the design code? I was taught never to have an isolation valve on a relief line. If you need to isolate the relief valve for maintenance with the system live, you need a duplicate relief systems with a three-way valve so that one relief valve is always connected.
Well, that's certainly good advice. If you want to be able to maintain the relief device while online, you could use a three-way valve or have two separate relief devices where one is isolated at any time. That's certainly an option. You could have a one singular relief device online with a valve for isolation for maintenance, but the valve would have to be locked open to make sure that valve is always open when the system is actually in operation. That's another way of doing it, and of course you need to be very careful that that valve actually is locked open when the process is running. So I'm not sure that would be outside of the code, but it would certainly be, you'd certainly need to at least lock open the valve. And as you said, I think a better solution would be to have multiple relief devices on a three-way valve so that you can perform maintenance on those relief devices while the system is running.
Right. We've got another question from Mohammed Abdul. Would you have a pressure spike on the low pressure side when the high pressure fluid leaks into here?
Well, so the EI guide talks about the surge you will get, that pressure spike you will get in the leakage event, and it goes towards the worst case of a shell and tube exchanger and the tube actually shearing, so you get the full area. And to work out that surge pressure, there's equations given in the EI guide, and that will be based. It's quite involved equations with a lot of parameters in there, and one of the parameters in there will be that area of the tube that you've got. And of course, if that area is greater, you're going to end up with probably a higher surge pressure or spike pressure in that event. Other factors obviously go into that. So the factors like the coefficient of discharge and the shell area. If you're only talking about a small amount of leakage, then you would need to account for that in the equation somehow. So maybe you might say, well, we're only going to have a proportion of the tube area actually with material leaking through, and that will then mean you've got a lower spike pressure. So that's how that would feed into working out that spike pressure. So if you go to the EI guide and consider what your worst case is, and you can do a sensitivity analysis. You can say, well, if this is my area for flow of the gas through from the HP side to the liquid side, what's my spike pressure going to be? Yeah, if it's just a small amount of leakage, it's not going to be such a big spike.
Right. There's another one from Mohammed, and he says, how to determine the initial surge pressure on leakage?
Yeah, so I guess I've answered that with my previous question. So
right.
There is an equation given in the EI guide for working that out. And as I say, it's quite an involved equation with a number of different parameters. It's worth saying on that it uses a term called the characteristic shell area, which kind of looks at the amount of area of the shell that's available for flow of the gas through. And that takes away the area that the tubes take up in the cross-sectional area. But it's obviously a bit of a simplification. There's also a coefficient of discharge term in there, which it can be a little bit difficult to ascertain. It will be determined. It's a number between 0.6 and 0.975 somewhere, and it's determined by the resistance to gas exerted by the liquid as the gas comes on through into the LP side. So initially, the resistance to the flow of the gas will be quite high because it's having to push that liquid through. But as the liquid is pushed through, you have more gas in the LP side, and then the coefficient goes higher. so there's less resistance. The point I want to make here is that if you've got a very complex geometry, or it's complex to work out what that coefficient of discharge is, then the equation given in the EI may be too simple for your purposes, and so the alternative there is to go for a dynamic analysis, dynamic simulation of what's actually going to happen. This is obviously a much more complex undertaking to work out the amount of flow you're going to get and what the surge pressure is going to be. So that's the reason why there's the equation in the EI, so it gets you away from having to do that dynamic simulation. But the dynamic simulation is an option if you really want to work out, I guess, more accurately what your surge pressure is going to be, and that would be particularly if you had a very complex geometry in your exchanger.
Right. There's another one now from Christy Hurst. It says design pressure versus test pressure and the 2/3 rule, which he's talking about. What pressure should the relief valve be set to open, e.g. on the LP shell side of a shell tube heat exchanger? Should it be the design pressure, test pressure, or somewhere in between?
It would be the design pressure.
Design pressure, okay.
Yeah, so you don't normally want the pressure in your equipment to go above the design pressure. So the relief valve would be set at, or the relief device would be set at no higher than the design pressure. You may choose to set it lower, or as I mentioned in one of the early slides, you may have different relief devices for different scenarios with different set pressures, but you wouldn't set them above the design pressure. But I guess in the tube failure scenario, you're imagining quite a serious event occurring. So therefore, you're thinking about, well, if I do go above design pressure, at least it doesn't go above the test pressure. So it's like another sort of layer of protection, if you want, thinking about that in that scenario. So it will have been tested to above design pressure, but the relief device would normally be set at no higher than design pressure. So you try and avoid going above. It would be, you would say that if you've got a relief valve, the relief valve will start to open at the design pressure, and you would say it would be fully open at 10% above the design pressure. So that you would normally call the relieving pressure. So that would normally be 10% above design pressure, and the codes would say that would be acceptable.
Right, okay. We've got a last question now from Colin Well, and he said, can I suggest that the location of the relief valve must also be considered? And it clarifies that by saying distance from the equipment must be considered. That's the location of the relief valve from the equipment.
Yes, absolutely. So sometimes it's necessary to put the relief valve, or you may find in old designs or existing designs, the relief valve may be on pipe work, not directly on the shell of the exchanger or the LP side of the exchanger. And if you're doing that, then you need to think about the consequences of that. So that will mean there's more time before the relief valve or the relief device will open, which would need to be considered. And also, if you're thinking about with relief valves, there's only a limited amount of pressure drop you're allowed from for the inlet to the relief valve, so that you don't get things like fluttering and chattering of the relief valve occurring. And that's 3% is normally the figure for 3% of the design pressure or the set pressure of the relief valve is the allowable. So if you're going to have the relief valve set or located quite a long way from the source of the high pressure material coming through in the tube failure event, or whatever event it is, it could be fire, say, then you would need to think about that 3% rule and consider that. So yeah, absolutely, that's a factor that would need to be considered and thought about.
Right. I'm going to have to close this out now because we're running out of time. So I'd like to thank John for this very interesting talk on pressure relief for heat exchangers and describing all the various failure modes in the case studies, which I found very interesting. I would like to mention that the IMechE is holding a seminar, Fouling of Heat Exchangers, on the 30th of November, and the contact is Robin Sarfus at IMechE.org. So if you're interested, you could register for that. So and thank you all for coming along and for your attention. We hope you enjoyed this event. Thank you.
Thank you.